Hi guys, welcome to my YouTube channel, and this is another one of RT Dowlett lectures on magnetism. Now today we'll be looking specifically at the magnetic field patterns around current carrying conductors. So if you consider a long straight wire carrying a current and you place a plotting compass near it, the plotting compass becomes deflected. Now the reason for that is there are a lot of charges that are flowing in the conductor. Now these charges are electrons, and as they normally move, they have a spin, and that spin is what generates a it's a force field, and we conceptualize it as a magnetic field. When we talk about this concept, it was discovered by Ørsted, right? He was a scientist. Now in this lecture, so now we'll be looking at magnetic field patterns around different conductors. And one of the first is a long straight wire. There are two symbols that you could use to represent it. You have a circle with an X, which represents a long straight wire carrying the current into the page, or a circle with a dot where the current is coming out of the page. Now both of them, you're going to have concentric lines representing the field pattern, and there are two ways that you could determine the direction. Right, the first is using your right hand grip rule. So take your right hand and curl your fingers down such that your thumb sticks out. So your four fingers from your index finger to your baby finger will be curled downwards, and then you have your thumb sticking out. Take your thumb and point it into the direction. Either you're pointing it away from you or you're pointing it towards you. If your thumb is pointing directly in front of you, then that shows that the thumb represents the direction of the current, which is into the board, and the curl of your fingers will tell you the direction of the field. So that would indicate that it is in a clockwise direction. Consequently, if you want to get the current going out of the page, your thumb is going to point towards you. So the curl of your fingers will now be in a anti-clockwise direction. Another rule is Maxwell's screw rule, where you could point here again, you're using your right hand and you're pointing the tip of your fingers as if you're screwing in a light bulb, and you rotate your hand in the direction that you were screwing the light bulb. So your fingertips would point in the direction of the current. So if you rotate your hand for current going into the page, it's in a clockwise direction, and the same way if the current goes out of the page, it is anti-clockwise. Now another conductor is called a solenoid. Now a solenoid is a fancy name for saying a coil of wire, right? So what I like to do is when I show students a solenoid, I show them the current going in the wire like this. So we're going to have a different color for the back of the wire. So the current goes down to these parts here would represent the back of the wire here. Right? So let's look at the current now. So the current is going here. It is going down the back of the wire. Down the back of the wire, and then it is going up the front of the wire here, right? So let's do that again. So the current is going down the back, up the front, down the back, up the front, down the back, up the front, and then so it's going basically in this direction, like here. So what happens is that we are going to now use the right hand grip rule, but this time your curl of your fingers, right, from your knuckle to your nail would represent the coil. That is the current flowing in the coil. So it's like I'm grabbing the coil, so my current is going down the back, up the front, down the back. So my current is going from the knuckle to my knuckle all the way down to the tip of my nail. My current is going down that direction. So it's like I'm grabbing the coil down the back, up the front. So now you are seeing that your thumb indicates the north pole in this direction. Now your solenoid typically has a field pattern similar to that of a bar magnet. So the current goes out of the north into the south, and then it goes north to south. Okay. All right, let's look now at a flat coil. So a flat coil would look like something like this, right? So it consists of two wires so it's like the current comes out and then the current goes in. So here you will find that you will just show the field patterns. So remember, here the field would have been anti-clockwise and here it would have been clockwise. So to the center, the field lines tend to follow each other. Now let's say that I have a two U-shaped magnet and I have two poles, north and south. So my field lines are going like this. And let's say I stick in the middle a wire carrying the current into the page, right? So around this, you're going to have a series of circles. So as I established before, just do this a little better for you, sorry. All right, so we have our north to south, and then here I have my current going into the page, right? So it's in a clockwise direction, and what you're going to notice is that here the field lines go in the same direction, but here the field lines cancel each other out because they flow in opposite directions. Guys, when they flow in opposite directions, they will tend to cancel each other out here, and you would tend to have a force. So let's talk a little bit about that. If you take a wire and you place it perpendicular, so if I have the poles of a magnet here and I place a wire carrying the current, it's perpendicular to the magnetic fields, right? So what you will find is that you have a force being generated. Why? Because your bar magnet would have its external magnetic fields, which are force fields, and then if you place a wire perpendicular to those force fields, the wire would have an associated magnetic field once there is a current flowing. Now these two magnetic fields are on the wire carrying the current, and also when it is placed perpendicular to those magnetic fields, those two magnetic fields will now interact with each other. So when they interact with each other, they will produce a resultant force. Now, one of the ways of determining direction, because remember, force is a vector quantity, one of the ways in determining that direction is by physically drawing out the field patterns. So you can look and see where the field patterns of the bar magnet coincide with the field patterns of the wire carrying the current. And if they tend to cancel each other out, that is where the direction of the force exists, where the field lines of each are opposing each other. Because the ones in the same direction will reinforce each other. Now, another way is by Fleming's left-hand rule. Now, the thing is with Fleming's left-hand rule is that you must have your conductor being perpendicular to your field. So you take the first three fingers of your left hand, that is your thumb, well, you're going to use here as your second finger. Then you're going to have your first finger, which is your index finger, and then you're having your thumb. Now these three are mutually perpendicular to each other. The thumb represents the force, the first finger represents the field, and the second finger represents the current. So you have current, you have field, and you have force. And all are perpendicular to each other. So if we go back here to this diagram, you would see that my index finger goes Right, so in this diagram, let's basically apply the rule, right? So your index finger goes north to south, your current goes into the board. So your index finger will be pointing to the right, your middle finger will be pointing towards the screen, and your thumb will point down. So it indicates basically here that your force is exerted down. And if I wanted to, kind of simplify this diagram, I could show that the field patterns are reinforced at the top, and of course my force points down.